Lover feeder.
Leader, feeder. I'm going to say word pairs. You repeat the word pairs.
Hello, Leah.
Answer 8 + 2.
Hello, Professor. Good morning.
Morning. How are you?
Try
Are your kids having classes?
good.
Yes, that's why I mute myself.
Yeah. That's okay. Yeah. You can mute.
Okay, thank you.
6 +
Oh, there's someone. Hello, Luke. Well, it seems like it's only you two. This is the hangover from the exam. How was the exam? Any comments on the exam?
So our next word for this week is the word you. You. See if you can remember how to spell you from yesterday.
Luke, any comments on the exam? I think you're muted, Luke. I cannot hear you.
Yeah.
Oh yeah, now it's good.
I was mostly thinking, but I thought it was okay. I feel like I had a little bit of a crisis just because I realized that I guess I've like when you're taking a divergence in non-Cartesian coordinates, I feel like I've been doing that wrong, or like I feel like in all my previous courses, like either I've been like told like use this formula or I've done it wrong. And I don't know. I'm not sure why I never was able to do that, but
But if I understand you correct, now you've figured it out, or
I
are you
think so,
still-
yeah.
Okay, yeah. You don't want me, do you want me to go over it or anything? No, right?
I think it's okay. I think I don't know. I think I was mostly just like overthinking and confusing myself. But
Yeah. If you think it can be productive for everyone, yeah, feel free to mention it again another time or even now.
mhm.
Was there a question about the exam?
No, I was just asking, how did it go? And Luke was just mentioning that, how would you state it? Like he was just showing his concern, I guess.
Yeah, I don't know. I guess I've been doing like spherical divergence wrong because I guess I would always just like look at I would always just do it like a naive dot product, or I would like use straight from the formula, and I wasn't really sure where it came from. So I guess like I used that. I had to look into that because I was getting my answers wrong. But after that, everything worked out. Yeah.
Moses, how did it go?
I would say I had the same, that same initial, I guess, incorrect, naive assumption about the divergence. And then, with number 2, I just was beating my head against the wall for a long time.
The cross product? No, this is not the problem. Number 2, what is
No,
number
number 2 had the 4 identities. One of which you had to use the divergence theorem, and the other you had to use the Stokes theorem to show the identities with the delta functions. I mean, I guess like intuitively I could grasp what was going on, and I could get something that was close, but I just wasn't super confident. Like basically the step of inserting the delta function into the identity, I wasn't confident that I was doing that, very rigorously. So, I still haven't figured that out.
Okay. Yeah, I see the challenge there because we are always used to algebraically going one step to the other, and delta function involves a little bit of, I would say, interpretation and how do you put it? It's not algebraic, put it. Yeah.
Mm-hmm.
Geometric also in a sense.
Yeah.
That divergence involved, I can see that. Yeah. But that's the practice, I suppose. But overall, from what I hear is that it helped to point out certain, basically, whatever Luke is saying, and I think what Moses, you're also saying is that when you take a divergence, always you take things for granted most of the time. And when you realize that there are these vectors that depend on coordinates, that's the point, I guess. And that's what basically general relativity is, a very sophisticated way of doing this. And of course, the physics is that you connect this to the acceleration. Michael, any comments?
Yeah. Pretty much what Moses said was that for the identities, I didn't know which step to insert the delta function.
Okay.
And I couldn't get one of them exactly right, like the curl of the phi hat. I couldn't get the z hat
Ah,
along with the 2 pi delta function. And
I
that was pretty much it.
can go over these things, but is the exam, when was the exam due, by the way? Is that due
It's due tonight.
tonight? Yeah, so I cannot discuss it now, right? Because
Right.
or what I can suggest is a hint is that whenever you're worried about the vectors or a coefficient, just integrate it. And the left-hand side should equal the right-hand side. Like this is a differential statement, make some integral. For example, if it's Stokes theorem to an area, if it's a divergence to a volume integral, and left-hand side should equal the right-hand side. So that might take care of a lot of, I don't know the vectors will come out like that or not, but usually the numbers come out. I think that's what I hear from both Moses and even Moses pointed out that where to insert the delta function. So usually that constant is the challenge, but then you integrate it and fix that constant. You say that it's an arbitrary constant, but then integrate it and fix it. So try that out, maybe that helps. And if necessary, we can go over it again on Thursday. Now I think it probably is not appropriate to go over, I suppose. And we are missing people, right? 1, 2, 3, 4, 5, 6. The 2 more people, Jordan and who else is it? Who else is in the club?
Khaled's not here.
Who?
Khaled?
Oh, Khaled. Yes. Yeah. Yes, okay. Yeah. So, yeah, so shall we proceed and do something, or are you guys too much having a hangover from the exam? How far did you go with the exam? Even now we're working on the exam?
I'm still on number 1, but I have the rest of it finished.
Okay.
Yeah, I mean,
Moses?
I'm not satisfied with what I came up with for number 2, but yeah, everything else is pretty much done.
Aliyah, you submitted it, right? I saw one submission. I think it was Aliyah.
Yes, I did submit it.
Yeah, good. Any comments on the exam? Yeah, I did ask you.
I think the same what they say delta function. This is the biggest problem.
Delta function. This is going day after day. So I have to do something about this. It's not good. Okay.
All right, we're going to erase our board and we're going to do one last whole.
I did it, but I'm not sure about my answer.
I see. Yeah. Yeah, I usually don't get these comments, by the way, that delta function is a challenge. I think maybe I don't ask these questions either in the first few weeks. These things come later, actually.
Oh, he's got with cat. Just beyond us.
Maybe. Yeah.
Right there with him. I can see him in our picture. Okay,
So let's, shall we do something light, and we want to go into the derivative on a complex plane. Shall we do something a little bit, or are you guys wanting to take a break or something? Like we did have a class during the exam day last week, so I'm going reasonably well with the pace. I think so. It's first plan. So shall I do a little bit, or do you guys want to take a break? You guys seem because all of you guys came 5 minutes late, and you guys seem too exhausted. So you want to take a break? Feel free. No issues.
I'm fine with either.
Okay, so Moses.
I'm also fine with either. I mean, maybe we could do a shorter class.
Yeah. Okay. So that sounds. So Aliyah,
Me too.
No, no one wants to say anything. Luke is. So, okay,
Yeah,
so
that sounds good.
okay, let me make it something short, and I won't get into the main idea in complex analysis is the idea of analytic function. It's basically the derivative of a complex function. So I won't get into that. I won't even begin that. But let's do something on multiplication and division, basically the organ diagram on a complex plane, which is very similar to the idea of polar coordinates. So, so, so we did talk about that. So this is a complex algebra, or what do you call this? Complex numbers? By the way, how is the pace of the course? Is it too fast? Is it too slow? In general?
I feel like it's fine.
Fine. I can keep going this way. Alia, you think I'm fast or slow?
No, I think it's fine.
And 206. Ooh.
Yeah.
And I know Miss
Anyone thinks I'm slow? It will be nicer that you cover more topics by going faster. Does anyone think like that? Moses? Luke?
I mean, that's fine. Yeah. I mean, I guess I noticed, like, not everything was covered on the exam. Like there wasn't any transformation of tensor stuff, and there wasn't any stuff on covariant and contravariant basis vectors. And so it just, I guess, like, I want to make sure I understand that stuff well. And so, yeah, I guess that's, like, that'll probably come up again later, right?
Probably not. So the point is, see, what happens is that unless you're doing general relativity, you might not see it.
Okay.
Most of the times, it's not even covered in a graduate school. Idea is necessary, yes. You might see it in a mathematics course, but the curvature and other things, you don't see it. So that's what I wanted to construct a problem, but I failed I never got to doing it properly. That was straightforward. So that it gives an idea. And I didn't want to make it just mechanical work.
Right.
What kitten?
Okay.
But I think I'm glad, after hearing your comments, I'm glad that I did give the divergence, because the divergence and the Laplacian basically replace that problem. So now, after hearing your comments, I'm glad that I did it, because it seems like you guys did gain out of it. And that is much more important. That's there everywhere. But of course, it is always done using always a textbook has it on the cover. So all the formulas are divergence and Laplacian always there on the cover, and you use it. It's good to have it at least once in life, realize what is going on. I mean, it's really, even otherwise you can survive without it also. So hopefully all this is useful. Okay, so complex numbers, we said, is a set of two real numbers. So this z is x plus I y, where I is equal to square root -1, and with the idea that I square is -1, I square is -1, and so on. X and y are real here. And this can be seen on a two-dimensional plane. So x is called the real part of z, and y is called the imaginary part of z. And any complex number is pretty much like a vector, if you want. So this is z, that's your y, that's your x. We defined what is called a complex conjugate of a complex number, which is x plus x minus, right? So simply replace that I with it, minus sign. And in general, we have z1 star times z2. It could be the opposite also, z1 times z2 star also is defined. You simply multiply. This is x1 minus I y1 times x2 plus I times y2. That's equal to x1 x2 plus y1 y2 plus I times x1 y2 minus of x2 y1. Nice thing is that if I were to do just one the complex conjugate of the complex number itself, z star times z, in that case x1 and x2 are the same, y1 and y2 are the same, and we get x squared plus y squared. That's the real part. And the imaginary part is actually 0 if x1 and x2 are the same, y1 and y2 are the same. Imaginary part is 0. And if you look at this diagram that I've drawn, this seems to be the hypotenuse of this quantity. So this is defined to be the magnitude of the complex number squared. It's equal to x squared plus y squared. So magnitude of the complex number will be x squared plus y squared square root. Looking at the diagram, it is clear that this is a right triangle there, and that's the hypotenuse of the triangle that I have drawn. And when we think of it in polar coordinates, this can be thought of as the radius of this, or the magnitude of z, we will represent it as r, let's say. So that's r. And immediately, we also know that that is an angle theta, so we can define an angle theta. And this will be measured, again, like in normal two-dimensional coordinates, you can measure it with respect to any line. Angles are always measured with respect to a certain line in a particular direction. It's often measured counterclockwise with respect to the x-axis. And if you were doing vectors, you would call this the cylindrical polar coordinate, and angle theta would be the polar angle. But here we will call r is the magnitude of the r here would be the magnitude of the complex number or absolute value, magnitude of complex number of z, and theta will be the, what is theta called?
The argument?
Argument. It's the argument, correct? Yeah. Argument of the complex number Is there anything else? Any other name? Yeah. Theta is the argument of the complex number. Yeah. Something doesn't ring a bell. Argument of Z. Just from the geometry, it is clear that R goes all the way to infinity, and it can be greater than or equal to 0. And theta, notice, has to be less than 2 pi and greater than or equal to 0. So theta is restricted strictly. Again, the same as polar angle. But here it plays this periodicity in a sense, and theta plays a significant role later on in complex analysis. Yeah, so that's what it is. And I should tell you that this is called the Argand diagram now. Whatever I have done just now, it should be pretty straightforward for us when we have seen a good bit of vectors. But this representation of a complex number in terms of R and theta took about 300 years to come by. And that made a significant difference. And without the diagram, they were all in the dark. It was not at all clear how to do things. There was a lot of confusions associated with it. But we can pretend that we have our diagram from the beginning. So a complex number Z is equal to X plus IY. Now, in terms of R and theta is R cosine theta. X is R cosine theta plus I times I R sine theta. That's good. And you immediately come across this to be R times cosine theta plus I sine theta. That's good. But it turns out that, again, let's pretend that, okay, now how do we see this? Let's remember that we're pretending that we are new to this complex plane. So we are, anytime there is a complex number coming in, we are try to do it from the scratch. So it's very easy to use things that is already available, pretending that, oh, this is also true for complex numbers. So we have to make sure that we verify things. So whenever there is so theta here is real, let's ask what is cosine of theta? Cosine of theta, or any function for that matter, is defined using a series. A Taylor series is a unique way of determining it. Unless and until there is a divergence at that point, it is well defined using a series. In fact, cosine theta is a short form for a series. You start getting lazy to write like that the whole series. So what is the series representation of cosine theta? It is at theta equal to 0, it is 1, so it should start from 1, and it goes as theta squared over 2 factorial plus theta 4 over 4 factorial minus so on. It alternates in sign, and they're all even powered. Same thing with sine theta, but this starts with theta itself, and then there's theta cube over theta factorial plus theta raised to 5 over 5 factorial, and so on. And you see that nice combination there, that this seems to be all even, this seems to be all odd, and there seems to be some connection between the two. So now that we have these two series, let's think of what happens if theta was purely imaginary. So let's ask what is let's ask what is, am I doing this correct? Yeah. Yeah, let's ask what is cosine of I times theta. So we do know that this is true for real numbers, but let's try to extend this to what if you have instead of theta being real, what will happen if it is complex? And we can do it because we have defined multiplication, addition, and subtraction and division of complex numbers. So whenever there is a multiplication, if we obey those rules, we are good. So then we know how to do cosine theta also. So this is equal to 1 minus I times theta square over 2 factorial plus I times theta all raised to 4 over 4 factorial and so on. But I square is equal to minus 1, so that kills the minus 1 here. That's 1 plus theta square over 2 factorial. This is I raised to 4 is again 1, so that's theta raised to 4 over 4 factorial and so on. So all the signs have been switched, so it becomes a positive series of even coefficients or even powers. Let's do the same thing with sine of I theta. Yeah. So sine of I theta similarly is equal to, so I times theta. Again, do the same thing here. There's an I cube over 3 factorial. I cube, pick out an I, or let me do this in 2 steps. Factorial plus I times theta is 5 over 5 factorial and so on. Clearly, there is a factor of I in there. That's I times theta plus theta cube over 3 factorial plus theta raised to 5 over 5 factorial and so on. And actually, I should also say that this is also cosine theta, right? It seems like cosine of I times theta is the same as cosine of theta. Sine of I times theta is equal to I times sine theta. So if we add them together, so notice we have this cosine theta plus I sine theta. So cosine theta plus I sine theta is the same as cosine of I theta plus I times cosine of plus sine of I times theta. Or if I look at the series, I see that why am I messing up something? How? So yeah.
I don't.
So
Oh.
yeah, go ahead.
I don't think cosine of I theta equals cosine theta, because that, like the cosine of I theta series doesn't alternate.
Oh, yeah. So maybe that's what I'm getting confused here because I'm not seeing that answer. Okay. Yeah.
Yeah.
So this is not cosine theta, right? This is not cosine theta. Yeah. Thank you there. And same thing here, right? Then so this is also not correct. Right? Okay. This is fine. Now, better. Better. Okay. So. So what do I want to do?
I think you just want to multiply sine theta by I and then add the two series. I think that's more straightforward.
Yes, I don't have to do all the gymnastics you're saying.
Are you trying to relate it to the exponential series?
Yeah, the standard things, right? Yes, exactly. Yeah, so you guys have all seen it. Aliyah, Moses? But we have to do it. Okay, so
Yeah.
let's.
No,
Yeah.
I mean, I know where you're going.
Yeah, you guys know where I'm going, so I'm struggling here. Okay, so let's see. So I don't do all this. So let me erase all this. I don't want to do it. I guess the proposal is that just start from here and just multiply the I here, correct? Yes, yeah, I think put the I in there. Yeah, I think let's see what you yeah, let me change this. Okay, change the strategy. Yeah, thank you. So we want to deal with this, correct? So cosine theta plus I sine theta is equal to 1 minus theta squared over 2 factorial plus theta raised to 4 over 4 factorial minus and so on. And multiply an I, and you have theta minus theta cubed over 3 factorial plus theta raised to 5 over 5 factorial and so on. Change this a little bit. Introduce, because I square is equal to minus 1, I raised to 4 is equal to plus 1, and I cube is equal to minus I, and what else is there? I is equal to I. So use those features in there, and I can get this is 1 plus I theta squared over 2 factorial, and this is plus I theta raised to 4 over 4 factorial, and so on. This is the first line writing out. And in the second line, I have plus I theta, introduce the I in there. Here, write this as I square, and there is another I get this as I theta cube over 3 factorial, and so on. This is the principles. And one sees that this is a total series now. 1 plus I theta plus I theta squared, and then cube, and that's the pattern there. And that's nothing but the series for the exponential. Right? Usually exponential is defined for real, but this is the you introduce the imaginary times the function x. So that's equal to e raised to I theta. So this is equal to cosine theta plus I sine theta is equal to exponential of I theta, and this is there's a name associated with this. This is called de Moivre's. De Moivre, how do you pronounce that? I think it's capital D. Theorem. And that simplifies things a lot, as you will see in a minute. If we use this back in there, suddenly a complex number is, oops, it's r times e raised to I. The complex number has two representations. It's either x plus I right or it is r times e raised to I theta. This is in vectors. If you were to look at this, these are the component form. When you're doing addition, subtraction, it's best to do it in the component form. And if you're doing it in multiplication, at least in complex multiplication, we will see that it is best to do it in this form. Okay, so that's what. Any questions? Sorry about the small tangent. I was not sure what I was doing myself. Okay. Any questions here? This should be, as you guys have saying, you guys have seen this before. Okay. So let's do how things work in multiplication. So first of all, this immediately raises the question that what do we mean by, like there was a question raised, or I mean it's, yeah, so z is equal to x plus iy is r times e raised to I theta. That's the representation. And example is examples is what is I? I is also a complex number. Its magnitude is 1, and its argument is pi by 2. So it is e raised to I pi by 2. That's what the imaginary. This is the I. That's a primary additional quantity in complex numbers. What about -1? Now we can write -1 as this is -1 plus I times 0. And immediately on the complex plane, you see that this is actually down here. Its length is 1. It's making an angle of pi degrees with respect to the x-axis, and you would say this is exponential of minus pi. Minus I, this will be down here, right? Minus I is here, so it will be exponential of I times 3 pi by 2. If you want, it is also equal to exponential of minus I pi. And that's because exponential, so here we have used, note that exponential of I times 2 pi is equal to 1. So I can add as many 2 pi i's as I want, and things don't change. So that's a ambiguity that comes in, and it will play, or it plays a significant role when we are interpreting complex analysis later on, especially later on when we start doing integrals and all. This plays an important role. What else can I point out at this stage? Yeah, so let's talk about one of the points we made in the last class. There was a confusion as to what is square root of -2 times square root of -3. I haven't introduced square roots yet, so that could be, maybe I'm doing this early, but let me attempt to this anyway. Whenever there is a confusion, convert the number into the Argand diagram, and this would be exponential or 2 times exponential of I times phi. And the same thing here. This will be 3 times exponential of I times phi. And one should be careful here that there could be this 2 pi also in there. So we have to worry about that. So maybe a more formal structure of this will come later on when we define the roots in a proper way, including all the roots. But at this stage, it is roughly clear that now if I had to do this, this is 2 times 3, so that's 6 times e raised to I q pi, and that's equal to the square root of 6 times e raised to I pi, and that's equal to minus square root of 6. Whenever we take a square root, there are more possibilities, and we will talk about that when we do the real square root, which we'll try to do in a few minutes. But let me first go and before I come to the square root, I actually do the multiplication. So multiplication of complex numbers, multiplication product of complex numbers. If I'm doing z1 times z2, this is we last time showed that we can write it in terms of complements, and that has a structure. But now there is an easier way of doing this. So that is R1 times e raised to I theta 1 times R2 times e raised to I theta 2. I just try to multiply these quantities together, and it turns out that this is simply the multiplication of the magnitudes R1, R2, and the exponential, the arguments combined. So this is exponential of I theta 1 plus theta 2. It has a nice geometric picture. So let's say this is theta 1. That's complex number z1. That's theta 1. That's r1. The length of that is r1. And I could have this is r2. So this is z2. So that's theta 2. What will be z1 times z2? Its magnitude is r1 times r2, and its argument is theta 1 plus theta 2. So I have to get a line which is making an angle of theta 1 plus theta 2. So I add this theta 1 in here. That's along this line. And presuming that r1 and r2 is larger than 1, then it will be bigger. So it will be somewhere here. So that's z1 times z2. And this is theta 1. If that is the case, there is a nicer way of doing. Let's just do z. Let's start with z, then let's do z squared, then let's do z cubed, and so on. So that's the case. Let's say this is z1. That's theta. Let's say the magnitude of that is greater than 1, slightly greater than 1. So this is 2 times theta. That's z. That's z squared. That's also theta. Z cube would be slightly larger. That's also theta. That's theta. 4 times theta, and you get bigger, 0 raised to 4. And 0 raised, so this is again theta. 0 raised to 5. And you get the pattern. It grows in length and its angle keeps. Oh, did I do this? Yeah, z cube. You keep adding theta, right? It's not 0 raised to 4. Yeah. Okay. That's multiplication. In fact, if the magnitude was 1, so let's consider the case z such that, so z, that is z such that magnitude of z is 1. And then let's again find out what is z, what is z squared, what is z cubed, what is z4, and so on. And it turns out, again, this time magnitude is 1. So we know that each one, since the magnitude of z is equal to r e raised to I theta, right? So r is equal to 1. So z is e raised to I theta, z squared would be e raised to I2 theta, and it's very clear that z raised to n would be e raised to I n theta. So draw a circle. Right, that's a circle. And start with some angle theta. Let's see theta. So that's z. Okay, arbitrary z of unit magnitude. And z squared would be double the angle. So that's z squared. That's z cubed. And that's z4. And so on. This will be z5 and so on. And we do know that based on whether this angle is rational or irrational, it will either start repeating itself, like if it was, for example, a integer or an angle which is 2 pi, which divides 2 pi into equal quantities, then this will, after one circle, it will start repeating again. But that's not necessarily true. If it divides the 2 pi into a rational partition, then it will go n number of times and then start repeating itself. And if it was dividing it into an irrational number of times, it will not repeat itself at all. So all possibilities are there. Right? So that's a nice way of looking at it. And this is the idea we will do to actually do the roots of a complex number. But before that, let's quickly do division. Division as z1 divided by z2. We immediately say that go to the polar form, and we have r1 over r2, and that is e raised to I theta 1, e raised to I theta 2. And this is the magnitude is given by the division of the two magnitudes. And the argument is e raised to I theta 1 minus theta 2. So instead of going clockwise, increasing the angle, you actually decrease the angle. And how much you decrease is decided by the one that you're dividing by. So for example, if you had Z1 here, let's see, Z1, and let's say Z2 is somewhere down here. Not sure if that's the most illustrative one I'm drawing. This is theta 1, and that's theta 2. I have to subtract theta 2 from theta 1, so I have to go the opposite direction. So theta 2 goes in here, so this will be somewhere. That's the line on which I will have my division of Z1 minus Z2, but its length is given by ratio of R1 and R2. Let's say R1 was larger, or R2 was larger than R1, so this will become small. So this is Z1 over Z2. With this idea in mind, let's define what are roots of a complex number. So, roots so let's say we have a complex number z is now I don't even write x and y since we are working with multiplication and division. It's convenient to just work with magnitude and argument. And we want to define what is z raised to something. In fact, this could be a fraction, and in particular, let's say we want to talk about, let's say z to the power 1 over 3, right? So this is cube roots of the complex number z. Let's begin by 2, right? So y start with 3. Z and you would say immediately do it on the right hand side also. So that's r e raised to 5 theta, and that's magnitude of or the square root of the magnitude. So that's half. But now, so maybe I should stop here for a moment and say that remember the point that there is an ambiguity in this argument definition, in the sense that e raised to I theta and is equal to e raised to I theta plus I 2 pi. For that matter, it doesn't even have to be 2 pi. It can be any number of 2 pi's. So let's say this is m times 2 pi, where m could be 0, plus or minus 1, plus or minus 2, and so on. I can add as many 2 pi's as I want, and the number is the same. So that ambiguity is there, and that actually plays a role in taking the roots. So before we do anything, before we make this operation of this square root inside, let's introduce this ambiguity. because 2 pi that is known, but when you actually divide it out into many pieces, then it starts playing a role. This is e raised to I theta, and this is I m 2 pi. Right, where m is the same quantity right here. And now we take the actual square root, pretend as if we are doing normal algebra. So this is square root e raised to I theta over 2. And now we have features here. So this is e raised to I m pi. It seems like there are lots of roots there, but let's see what are the values this takes. And let's keep this as this is. Or let me call this. Let me call this. Let me just for symbolizing this, let's call this Z naught. So it seems like the square root of z is equal to z naught or yeah, let me call this z naught half. So that is it. So this is one of the roots. When m is equal to 0, that's what I think we can pretend that to be. And there are more roots. When m is equal to 1, this is z naught half times e raised to I pi, which is minus 1. When m is equal to minus 1, this is again, so m is equal to 0 gives you this, m equal to minus 1 gives you this, m equal to plus 1 also gives you this. So this is for m equal to 0. This is for m is equal to plus or minus 1, both gives you the same number. And next one is 2. That's actually again gives you 0 raised to half. So this is m is equal to plus or minus 2. And do the same thing, z0 half, and then again minus 1. This is m equal to plus or minus 3. And you immediately see that they're all actually repeating themselves. So there's only 2 specific ones, and that we know actually. Square root is always plus or minus of or e raised to I theta half. That's what we have learned. So kind of elementary stuff, but now we know that square root, when we take a square root of a complex number, there are 2 roots, plus or minus. But what about cube root? Immediately we ask, what is the cube root of a complex number, and how do we do that? Any questions as of now? Should have seen all this, I suppose. Okay. Luke, questions you seem to be.
Yeah, is that a 2 in front of the, so the last line? Yep. That's a 2?
Oh no, this is plus or minus.
Oh, plus or, okay. That makes more sense.
Plus
yeah, I see.
Or minus, right? Either plus or minus, right? So that's
yeah.
That comes out.
Yep. All right, I'm all good.
Okay. Let's do a cube root and see where it seems like there is one point, if you notice, whatever number you're doing, this r, the magnitude is always the r raised to 1/3. And it is only the argument that actually is playing a role in this roots. So usually you say that forget about the r, let's set r equal to 1. Right? So you say, let's talk about, usually you say cube roots of unity, but let's say that you're talking about z is equal to e raised to I theta. So r is equal to 1. So basically, if there is an r, then all this you have to introduce this r raised to power, but that doesn't give you any multiplicity. That's just the nth root of that r. And let's ask what is, so the question is, what is z 1/3? So that's like asking the question of what is the complex number, so what should I call it? Yeah, u. So let's say, yeah, so if I'm interested in finding z of, is that what I'm doing? Yeah, so yeah, I'm asking what is z raised to 1/3, and we again do the same idea, right? So z is to 1/3 is no r. So here, so this is e raised to I theta 1/3, but I bring in the ambiguity. This is e raised to I to m pi. M again is 0, plus or minus 1, plus or minus 2, and so on. All integers. And this is e raised to I/3. And I get e raised to I 2 pi/3 times m. And let's again figure out what are its roots. Like each one of this actually satisfies this equation, but are these all different, or do they start repeating itself? So let's do m equal to 0. So then this is exponential of I theta over 3. When m is equal to plus 1, I have 2 pi over 3. So this is e raised to I theta over 3 times e raised to I 2 pi over 3. M is equal to minus 1. Actually, let me write this. Minus 1 is e raised to minus I 2 pi over 3. And so let's try to first see where these roots are, and then proceed and get other m's. They all have magnitude 1, so they will be on a unit circle, all on the unit circle. That's the complex plane. There is to begin with, there was a z. There was z here somewhere. That was z, but that is just a begin with. We started that. But divide that angle 3 times. This is 1, 2, right? So this is, that's your e raised to I theta over 3. So that's the reference line if you want. You can forget about the z to begin with. These are the roots, right? Because divided by 3 and you get the point e raised to I theta over 3. And now draw a point that becomes your reference line. 2 pi over 3, that's 120 degrees. So let me draw. So this is angle theta over 3. Theta over 3. Do the same angle here, that's a perpendicular line. Thus, and 2 pi over 3 is 120 degrees, so that's 90 degrees. So that's 120 degrees. That's also a root. This is e raised to I theta over 3 multiplied by e raised to 2 pi over 3. 2 pi over 3, 360 divided by 3 is 120 degrees. So I've added 2 pi over 3 to theta over 3, right? That's the idea of multiplication. And the third root will be do the same thing on this side. So that's 90 degrees. Go a little bit on the side here. So that's here. So this is e raised to I over 3 times e raised to minus I to pi. So it's, if you notice, this is dividing the circle into 3 equal pieces. It's like taking a pie and dividing it into 3. And now, but we didn't explore it completely. What about m equal to plus 2? M is equal to plus 2. This will be e raised to I theta over 3, e raised to I 2 pi times 2, so that's 4 pi over 3, which is 2 pi over 3 plus 2 pi over 3. So this is equivalent to, again, I will come down here. Right, so this is the same as the second root. So this is the same as this quantity. So it starts repeating. M is equal to minus 2. This will be e raised to I theta over 3, e raised to minus I 4 pi over 3. So 4 pi over 3 is 120 into 2. So that's 240 degrees. So I start from here and go back, and I come back here. So this is the same as this quantity. And you can show that as you proceed, all of them will start repeating itself, and they are all given in terms of these 3 roots. And there are 3 of them, and always in complex numbers, there will be the number of powers will actually decide the number of independent roots. This is equivalent to writing z cubed equal to a complex number. And the idea of cube roots of unity, yeah, so there should be an extra credit, right? So extra credit. Find the 5th roots of unity, let's say. Find 5th roots of unity. Unity means 1, so you start with just 1. That means to say that theta is equal to 0. You start from here. So I rotated this a little bit. So z is to begin with here. So theta will be 0. So everything is symmetric about that point. And let's stop here. I'm sure you guys have seen this, right? Moses, have you also seen it?
No, actually, I haven't seen all the way
Okay.
with the powers of M.
Okay, okay. But did it make sense?
Yeah.
So the main point is, if I've got anything past or anything, this is the important piece. I introduced this. So that actually gave it everything. Everything else followed from that. That wouldn't be obvious.
Mm-hmm.
And we'll do that again and again. In fact, Dirac quantization depends on this. Like it also is on this phase that it captures. So often, physics, there can be hidden physics in there. Or in the beginning, you tend to not notice it, and then you say, "Oh, there can be this phase," and you can find interesting stuff. Okay, that's all. Hopefully, it was not. It was lighter for right after the exam.
Yeah, it was good.
Okay.
Thank you.
Yeah, you're welcome. Okay.
See you guys later.
Bye.
Thank you. Yes. Yes.
Yeah. Bye-bye, Luke.
Bye.
Bye.
Bye, Elia.
Bye, doctor.
Bye-bye, Elia.
Bye.